Hey, how's it going? Welcome to episode 1 of BAMTV version 2. Why version 2? Because version 1 was terrible. No, but seriously, hey, my name's Phil Zito. I run buildingautomationmonthly.com where I teach folks building automation. And every week I'm going to be releasing a new video that corresponds with the podcast episodes that I'm releasing. So for those of you who are visual learners, for those of you who want to learn more about building automation, these are going to be some awesome free videos that are going to teach you a bunch of different stuff about building automation. Now you have to forgive my voice. I'm getting over a case of bronchitis, which freaking sucks, but neither here nor there. We're still going to have an awesome video here. I'm going to take you through BAS programming. So this is going to be part 1 of a 2-part episode where I'm going to start to unpack some of the programming concepts that I myself have experienced a lot of difficulty with, and I know others have experienced difficulty with. So in this episode, we're going to discuss what programming is. We're going to talk about points, different point types, different variables, things like that. We're also going to go through a 5-step programming process that has really helped me a lot in my ability to write programs, and I believe it'll help you a lot as well. And we're going to go through kind of what is line code, what is visual code, what is abstraction, some of these terms that you'll hear as you start to get into programming. And who knows, maybe we'll throw in a little bit extra stuff along the way. So what is programming? Programming, quite simply, is the tool or mechanism that we use to allow our controllers to take inputs, process the data from that inputs, and then command outputs. I mean, in a nutshell, that's what programming is. So you have what are called control systems, right? And control systems are just systems that allow you to control different process variables. Process variables being maybe a valve, maybe being a temperature, maybe being a speed. There's a variety of different process variables that you control, and you control them to set point. But how we do that, at least in the BAS world, is we use a controller, okay? And we don't use any specific magical type of controller. We use a form of controller called a DDC. And early on in my career, I didn't really know why this was important, but DDC, direct digital control, is actually really important. Because if you think about it, right, you've got a thermostat over here, and this thermostat is giving off a resistive value, right? So it's giving off a value in ohms. And then that resistive value is coming into your controller. Now the problem is inside this controller, there's actually a CPU or a processor chip. And that processor can only process what is called binary or ones and zeros. Unfortunately, from temperature sensors, resistance values are not ones and zeros. Like I said, they're resistance values. So we need a way to convert that. Well, what happens is in the DDC world, you have analog to digital conversion that happens on the input side of these controllers, right? So it takes a resistive input and it converts it to a digital signal. Now that's freaking awesome. And the reason it's freaking awesome is because it now allows us to write programs. We are no longer stuck in the crappy land of pneumatics. We have now moved up to the really awesome land of controllers and DDCs. Sorry, but not sorry to you pneumatic folks out there. You really need to get off that stuff. I mean, I don't know why people still sell pneumatics, but that's neither here nor there. Anyways, so with analog to digital control, now we're able to take in ones and zeros into this controller. And now with that newfound capability, we actually have to go and write programs. Now, in the very beginning days of this, you had what was called BASIC, which was a very basic form of programming. You know, if X, then Y kind of stuff. And that was a pain in the butt to write because it was line code. You had to write, you know, line 1, line 2, line 3. And then over time, what folks realized is that things like this if-else logic could be converted into a graphical block like a switch, right? So a switch takes a 2-state input, a 2-state command, and then it allows either input 1 or input 2 to pass through as an output. Now imagine inside this controller, you have all these different logic blocks interacting with one another. And when these logic blocks interact, they produce an output. And that output now goes and gives the controller the capability to go and command digital to analog outputs, because 0 to 10 volts, 4 to 20 milliamps, 24 volts, those kind of things that we are now able to command. So with this capability, we're now able to write programs that our controllers can do some awesome things with, okay? But here's the deal. Inside of programming, we have a lot of different variables that a lot of folks don't understand. They go to manufacturer training and they show up and they're exposed to concepts like digital floating points, analog points. They're exposed to integers, all these different kind of things that they've never experienced in life before, and they're struggling to keep up just with the manufacturer training and learn these new concepts as well. So what we're going to do right here on this side of the whiteboard is we're going to talk through these common points, okay? Because inside these controllers, you have four objects. You have inputs, you have outputs, you have variables, and you have logic. I've already shown you some examples of everything except for variables, okay? So when we're talking about this stuff right here, what we need to understand is that, okay, we've got our inputs, and these are physical inputs. These are things like resistive temperature sensors. These are things like 0 to 10 volt sensors that then scale to 0 to 100% relative humidity, things like that. We also have outputs, okay? So we've got sensors, switches for our inputs. I'm not going to write out every possible input. We'd be here forever, and that would be boring beyond boring. So outputs are things like actuators, things like relays, things like fan speed commands, okay? These are outputs that we're able to control. Then inside of this, and this is really important, pay attention to this. So these are physical points, okay? So when you hear physical points, these are physical inputs and outputs. You have a limitation as to how many physical points you can have on a physical controller. You can't have 400 physical points when a controller only has 10 or 20 points. You just can't do that. A point being a physical point, but we're also going to use that word point for other things like variables. Now there's tons of different ways to name variables. There's NVOs, there's AIs, BVs, AVs, MVs, AOs, like the list goes on and on and on. But the thing is that variables really fall into two buckets. Constants and, surprise, surprise, I really should think of a better name for this. Variables, woo! All right, but seriously, you have constants and variables. And this is where I see a lot of beginning programmers get in trouble, myself included when I first started programming, is you feel like, man, I got to do the customer right. I got to give them exposure to everything. And so in order to do that, I'm going to make everything a variable. I'm going to make it a writable. That's another way of calling it. So a writable, and constants being non-writable. I'll get to what that means in just a second. But I'll make everything writable, which means that it can be discovered and written to through the graphics. That's really bad, because when John the janitor comes along and he starts like, oh crap, so-and-so's cold or so-and-so's hot. What's this ilim? Oh, maybe that stands for temperature. I don't know. I'm just going to change everything. And I've seen that happen time and time again. And then quite often, these set points aren't being logged. They're not being trended. There's no historical reference to these set points. And so when they're gone, they're gone. They just get wiped out, okay? Now, that is bad. That's why in most situations you want to use constants. You only want to expose the bare minimum. This is called a customer independent programming style. There's really two programming styles, right? There's customer dependent and customer independent. Customer independent is where you keep most things constant so that the program can run independent of the customer. Short of them going to the fan and turning the hand off auto switch, they will be kind of protected from the program. I know that sounds kind of like we're dumbing stuff down, but we are dumbing stuff down, because the reality is, even though there's a fair amount of customers who understand building automation. They can't see what's inside the program, nor do they have a desire to see what's inside the program most of the time. And so we protect them from that by using constants. However, you have customer dependent code where you use a lot of variables. You'll see this in labs or college environments where you have a more sophisticated customer. Now, variables are really important because we're going to use them for our set points, okay? So for example, if I were to write some logic here, like I was to use a comparator and I were to say zn-t zone temp and then znt-sp zone temp set point, and I was to drive a output of this comparator. So what a comparator does is says, if this zone temperature, let's just say this is greater than in this case, if this zone temperature is greater than zone temperature set point, this is on, or it's a value of 1. What would I use this for? Maybe I use it to enable a cooling PID loop. But this is an example of logic, an example of physical points, zone temp being a physical point, and zone temp temperature set point being a logical or variable point. In addition to these constant and writable variables, you also have the ability to have global objects, which I cover in the podcast a little bit. I'm not really going to cover too deeply here. Actually, I don't want to say I'm not. I might, but I might not. So no promises, folks. This is completely unscripted. This is just how I teach. I teach raw, I teach real, and I give you kind of what it really is out in the field, because there's so much fluff and polished crap out there that is utterly useless to folks. And I want you all to have some useful videos that you can refer to that are really going to help you be successful. Okay, so inputs, outputs, variables, logic. We went through controllers. We talked about the written form of programming. Now, I mentioned earlier in the video that I would talk about a concept called abstraction, or at least I think I did. And abstraction is where we take this if, then, else kind of line code-ish stuff and we abstract it to a visual logic block. About 80% of the controllers out there that you work with are going to be visual programming. They're going to be graphical programming. Excuse me. Like I said, I'm getting over a cold. I'm sorry. I'm not going to edit this video, so you just have to forgive me. But as I mentioned, you've got these inputs, you've got these outputs, and it's all represented in this graphical block. So in this graphical programming software, what's going to happen is you are going to go and you're going to have what's called a stencil or a library or a toolbar, and you'll be able to use different blocks off that toolbar. That's why in the next video, when I go through logic blocks and I cover that, that is going to be freaking important. You need to subscribe to these videos because that video is one you do not want to miss. Because if you understand logic blocks and you understand design patterns, something I teach in my BAS programming course, you can work on any manufacturer's software. Folks have often asked me, Phil, how can you work on different manufacturers' programming software with such limited experience with that software? And it's because the logic blocks don't change. The design patterns don't change. Don't worry, I'll get to what design patterns are in the next video. But as I was saying, inside this controller, we have graphical logic blocks that, when pieced together, allow us to execute the sequence. Now, here's something I want to go through with you right here. And I'm going to kind of tilt the camera just a little bit so I've got a little bit more space here, and we're going to work right here, okay? And this is called my 5-step programming process, okay? So 1, 2, 3, 4, 5. If you come out of this video with anything, I want you to understand this 5-step process, okay? Because this 5-step process right here is going to make a huge, huge difference. The first thing is, whenever you write a program and you're reading through the sequence, you do not want to write line for line what's in the sequence. I made this mistake so many times and it totally screwed me. I ended up with this pile of poo program that I couldn't use, and it was just terrible. Because if you go line to line, I mean, raise your hand. Well, I can't see your hands, but imagine I could see your hands. How many of you have looked through a sequence and it starts off with supply fan, And then halfway through, there's another supply fan condition. And then at the end, there's another condition that completely counteracts the two conditions that came before. And you're like, what the heck? Because you're trying to write this program and you're having to rewrite it and rewrite it and rewrite it. And it becomes this bastardized piece of junk that no one can use. So that is why it's really important to have a process rather than just following along the lines and writing your code. I did that for about a year and a half where I just followed the sequence and wrote my code. And it was, oh my gosh, once I learned this process, it was like the heavens opened up and I saw the light and all the crappiness that I was experiencing with programming just went away. Maybe it wasn't that dramatic, but nonetheless, it did make a huge difference. So, bullet number 1, physical points. Whenever you start writing your program, you're going to want to go and take your physical points and add them to your wire sheet, your programming sheet, whatever you call it. Your inputs go on the left typically, and your outputs will go on the right. That's typically how you'll lay things out. Next up, we want our variables. Now here's the deal. I realize that you're not going to know all your variables because sometimes as you're writing code, you're going to find that you need to add variables because, let's be real, not all sequences have all the set points added to them. There's actually quite often several set points, both writable and constant set points, that are not declared in the sequence of operations that you kind of need to figure out on your own. So we want to add our variables. Next up, we want to do what's called Boolean code. Okay? Oh, this is a segue. I just realized I missed this. But like I said, this is unscripted. Boolean. Okay, so no, I think I covered it actually. Boolean is ones and zeros. Okay? It's true or false. It is a on-off state. You always want to write your Boolean code right after your physical points and your variables. And here's why. Okay? Think about it this way. If I told you you had a VFD fan and you needed to run that VFD fan to control static pressure, by the way, that's an analog control mode, how would you do that? What would you do? You would probably have to turn the fan on first, right? I mean, you could turn the VFD on all freaking day long, but if the fan's not on, it doesn't matter, right? It's not going to run. That's why Boolean code should always come first, because the Boolean code is going to be the start-stop, on-off condition that allows you to drive your analog code. You may say, but Phil, what about dampers? Well, even dampers need an occupancy command oftentimes before they start to open up, right? That's a Boolean code mode. Next up is analog. This is things like your valve commands, your damper commands, your speed commands. All the things that are analog, now you're going to start writing that code as well. So you've written your physical points, you've got your variables, you're writing your Boolean points, or your Boolean logic, you're doing your analog logic, and now we move to our safety logic. This was a huge one for me. I used to just write safety logic. And quite oftentimes, safety logic would get overridden because I'd write it, and then I would make a change with analog control, and that would override it again. So you always want to do safety logic last. Safety logic should be modified on top. So if you think about a layer, right, this is almost like a 5-layer cake with the physical being kind of the skeleton, the variables being the muscles, the Boolean kind of being the bigger muscles. I'm running out of examples for body parts here. The analog being the skin, and then the safety being like the protective gear. Okay, that was a horrible analogy, but nonetheless, you've got these 5 different steps that you want to take on every program. And I'm telling you, even if you're a doubting Thomas and you're like, I don't believe this could work for me, I just don't know. I'm telling you, if you go about using these 5 steps right here, it's going to make a huge difference to your programs. All right? It just is. Okay, so let's recap kind of what we went through here, right? Because we've unpacked a lot of topics in a very short amount of time. Okay, we started off with why DDC is so important. We talked about how there is a central controller inside, and inside this controller, there's a central processing unit rather, and it processes ones and zeros. It processes binary. So we need to convert our inputs to some form of digital signal. That way our processor can process it. We started off with line code back in, kind of the 70s, 80s, and we've moved to graphical representation, except for a couple manufacturers who refuse to modernize their products because they want to make it harder for their technicians, but that's neither here nor there. So, as I was saying, we've moved to graphical code for the majority of building automation systems out there, and this graphical code sits inside the controller. Now, one little segue, I've had this question quite a bit. Folks have asked me, why can't we just use someone else's graphical controller? Well, because inside this system, you have something called firmware, and this is really low-level code, and it allows for that switch from line code to graphical code, or from line code to basic instruction code that this processor uses. And because of that low-level code, that's why you have to use a specific manufacturer. Now, you're seeing things like the Sedona framework, and you're seeing things like the new Tritium controller that came out where they're pushing the stack down, where they're making an effort to use a common code framework. That way you can go about writing programs with the same software. And Lawn was hoping to do this as well with their kind of plugins for their lawn software. It didn't really ever catch on, unfortunately. But the reality is that's why you have to use custom programming software from every manufacturer, because their code base inside their actual physical controllers is different. And in order for that to ever be resolved, everyone would have to agree on a single code base, and they would all have to agree on a single firmware. And that's fantasy land. That's not going to happen. Now, from there, we talked about inputs, outputs, variables, and logic. That should all make pretty good sense. It's all pretty straightforward. And then we talked about how we take these kind of four things and we apply them using the programming process, which is we start with the physical layer, right? We do our inputs and our outputs. Then we move to our variables, realizing that we may not always know what variables we're going to work with. From there, we go through Boolean code first. Boolean being the on-off code, okay? And then from there, we move to analog code, which is our code for adjusting anything that is analog, anything that's 0 to 100, 0 to 10, et cetera, et cetera. And then we close out with our safety code. So that's it, folks. I really would love to hear your feedback on this new format for BAMTV. I think this is going to be much more engaging than those horrible live casts that I was doing with BAMTV version 1. I just was not feeling those. That's why that whole thing died on the vine. But this is much more my speed, and I'm feeling like I can connect better with you and communicate with you. I'd love to see your questions in the comments section. I'd love to answer your questions and be able to explore anything you're kind of struggling with. If this looks really awesome to you, realize this is just my free stuff. I really would encourage you to check out my Building Automation Programming Fundamentals course, where I go through in great detail the programming process. You get some programming software that you can work with along with a virtual controller, and you're able to really truly learn programming. I am bold enough to say that if you give me 2 weeks with that program, I will teach you how to program building automation systems. I've seen it time and time again. I've been around the block. I've got all the scars, and I can help you avoid the pain of spending years learning to program. Now, in next week's episode, we are going to go through logic blocks, and we are going to dive into how to digest sequence chunks, which is really, really important. I hinted at it in this lesson, but I didn't go into it, and it's going to be really important that you check that out. So hit the subscribe button, and you'll get notified as soon as my next video pops up. Thanks a ton for watching, and I can't wait to talk to you in next week's video. Take care. I'll see you later.